How do you exponentiate a matrix? By definition, it can be done by using the Taylor expansion, right? This is just the definition. So the exponent of x of alpha, m alpha is just a number, a scalar, can be complex number. M is a matrix. It's just equal to, by the definition, we remember e to the power x is what? By Taylor expansion. 1 over n factorial to the times x to the power n, right? Which means 1 over 0 factorial x0 plus 1 over 1 factorial x to the power 1 plus 1 over 2 factorial to x to the power 2 plus 1 over 3 factorial to the x power 3, right? Which is just 1 plus x squared over 2, x cubed over 6. This is the definition of the exponent, e to the power x. We use the same definition here. So if I have a general matrix, which is not diagonal, you can always find its exponent by using this method. It's the same if you want to take the log of a matrix, the sign of a matrix. You just use this definition, the Taylor expansion, right? So because of this, it becomes 1 over 0 factorial alpha m to the power 0. Just like this case, it's just like I'm putting x equal to alpha m, but now the m is matrix. Similarly, I have all this. And this is easy because a matrix times matrix is easy to evaluate. Eventually, it becomes the sum of many matrices. And this all together becomes the matrix representing e to the power alpha m. Okay? So this is the difficult, a tedious one, but it's always correct. You can always get it, right? Now, what if it is diagonal? Here, I try to show you that what I said earlier is correct. When it is diagonal, then I only have elements along the diagonal, right? So again, I can use the definition to expand it into the power series. Now, I use the index m instead, so that because I have a dimension of n plus 1. So this again is 1 over m factorial times the argument to the power m, right? So this one becomes 1 over m factorial, and do not forget that m to the power m, you just multiply the matrix m time. And it's a diagonal matrix. When you multiply to itself, it's just the same as the diagonal element raised to the power m, right? Just try it, okay? You just try to do a multiplication of a diagonal matrix to itself, right? You will see this. And if that is the case, then I'm just adding all these matrices together just with different m. So I can just put this inside, right? And as a result, what is this? This is nothing but just e to the power alpha m00, e to the power alpha m11, right? So this shows that if your matrix is diagonal, I can just exponentiate it by putting this exponential into the diagonal element, right? I was trying to exponentiate alpha m, which is a matrix, and m is m00 all the way to mnn. Now the result is just a matrix with exponential alpha m00, exponential alpha m11, exponential alpha mnn, right? And that proves why I can do this, because here I have a diagonal matrix. I exponentiate it. I just exponentiate each of the elements. So here I obviously missed the 0. Okay, so that is how you exponentiate a matrix, right? Now, what if your matrix is not diagonal from the beginning? What you can do is diagonalize it. And this reconnect to what we had in the previous video. You diagonalize the matrix, it means you transform it into the base is eigenvector basis. Because if you use the eigenvector as the basis, then the eigenvalue will be the diagonal element, and it will be diagonalized by definition, right? We have spent some time talking about that in the earlier of the book, right? So what we are going to do is we just transform this matrix, but let's remind ourselves again, what is U? U is the transformation matrix to bring from the old basis to the new basis. The old basis may be the basis of Z vectors, 0 and 1, right? And we transform to the new basis, it may be the plus and minus. So in the old basis, this sigma x is not diagonal, but after you transform to the new basis, it becomes diagonal, right? So that is what we learned before. Very easy to memorize. Each of the element is just the new basis eigenvector in a product with the old basis eigenvector. We get U, right? And then for the matrix, I told you before already, it is U dagger, right? So we transform it to a diagonalized one. For example, the sigma x in the 0, 1 basis, after you diagonalize it, it becomes 1 minus 1. Then you exponentiate. This is easy, right? And then you transform it back to the original basis. Right? For example, the O can be 0, 1 basis, and the new will be plus minus basis, okay, which will make the sigma x diagonal. Right, so we learned this because this is very useful in quantum mechanics, because Schrödinger equation has a differential term, and it usually is d something dt equal to itself very often. The solution will be e to the power of a matrix, right? You will see that very soon, okay? And this is just the summary. Finally, we talk about the rotation of the broad sphere, right? If you rotate in rotation on the broad sphere, how many rotations do I need to do in the 3D space in order to get back to the original state, right? We just take a special case and we show that we need to do 4 pi rotation, right? I forgot to bring the cup again, but you remember in order. This side I don't want to damage it because you have not finished. Right? Again, I need to do 4 pi in order to bring my cup back to the original place due to the topology. Okay? So that's it for the review. Any questions?